So, as you are who have attended the previous part, so we in last session will cover some part of basic aspect of battery, what is battery, how we perform the simulation. So today we are going to discuss about the thermal management of those battery with the help of cooling technologies and the PCM technology, how we can take the help of PCM or the liquid or the air. Liquid could be a water or it could be air. So how we are using different cooling technology to bring down the temperature of the battery, because as a mechanical engineer or as a battery thermal engineer we have to understand the point how much battery is heating and how we can reduce that temperature. So we'll see some recap part of last case what we have studied in first part, then we'll go with the cooling methods. Then we'll work on the liquid cooling with the laminar flow in single cells. I'll showcase you the hands-on demo. Then I'll showcase the case studies and the work progress, how we can set up the complete model on the prismatic cells or the cylindrical part. So we'll go with the PCM as well as the prismatic. So before proceeding further, we should know the cooling technology. I think most of engineers and the research scholars and students, you are familiar about the techniques we have in the battery cooling part. So we have liquid cooling, air cooling. So in liquid, we have the direct cooling and indirect cooling. Direct means the components directly placed inside the with the coolant. Like directly I'm putting the battery on, and batteries are immersed inside the liquid part. So that is immersion cooling. Then we have indirect, through which I'm not keeping the contact of liquid to the batteries, but they are taking away heat from the batteries with the help of some cold plate, jackets, or heat pipes. So that we do with the help of the liquid cooling. So mostly in these cases, we use water as a fluid or some kind of coolant gases, which are in liquid form. Uh, then we have air cooling. Mostly we have two methods. One is the natural convection. Then we have another forced convection. So generally, when we are doing the air cooling technology, we optimize a lot of things, like what should be the thickness of our fluid domain. If I'm putting some inlet cross section, whether I can increase my cross section or not. So a lot of engineers and the researchers have done a lot of optimization. So those optimization we can do with the help of parametric simulation. Okay, I will showcase if I vary the length, how I can make it as parametric, and then I can study the parametric simulation of that with respect to that part also if I change my domain length. So we'll take simple examples. I will just showcase with the techniques, but as we have the limited time, some results I will showcase with the case and data file also. Then we have PCM technologies, mostly for we know that phase will change when we are using. So what does PCM do? It's a phase change material. Like you can take simple example of our candle. So when we burn the candle, what happens? The wax will melt, and if we store that molten wax, what will happen? Again, it will freeze when there is no heating. Same way in case of batteries, the PCM will take away the latent heat from the batteries. It will absorb the energy, heat energy, and the PCM will start melting. So once the batteries are not operating, again it will freeze. So what is the advantage in air cooling and liquid cooling? We are giving the uh, liquid or the air with the help of some pumps or with some kind of external energy sources, whereas in PCM we don't require those kind of sources. So every technique have their advantage and disadvantage, so we'll discuss that part also. So if we come with the liquid cooling technology, so you can see here we have the channels. Okay, we are providing the coolant from one inlet direction, just like normal CFD flow. We provide the inlet and it will take away the heat. So in this scene, you can see it is not directly in contact. So there is a enclosed wall. So that is indirect cooling. So whereas if there is a direct cooling, like immersion cooling of batteries, we do sometimes batteries are inside the liquid, it is all over. So that is complete immersed cooling techniques. So the heat will get away. So these parts will treat as a heat exchanger. And the current example, if you see the Audis, Ford, Focus, GM, Chevrolet, Tesla, these industries, automobile industries, they are using this kind of liquid technologies. Then we have air cooling. So most of these industries, automobile industries or the manufacturers, they are using air cooling technology. So when we talk about the air cooling, we have two options. We can use the fan which is already there inbuilt in the car, and we can have the additional fan also for the cooling purpose. So they, when we are using this kind of cooling technology, there are some cases where we have some concern we have to focus about, because when we are talking about the this fan cooling, So the fan design is also very critical. So as a safety engineer, we have to understand how the fan is giving the efficiency. So what kind of fan we should fit on, and how much mass flow rate I can extract from the fan curve. So with respect to that, I have to see the cooling behavior. So they are well connected with each other. When there is a natural convection, I'm not putting anything. Natural convection, what will happen if the outer ambient temperature is very high? Again, hot air will come instead of cold air. And sometimes the condition might will come where I have to think of about whether I have to cool my batteries or I have to give the comfort condition to my passenger inside the car. So these are few concern. That's like other, we call it as active and passive concern. So generally these kind of concern comes when we use our liquid cooling technologies or air cooling technology, like the airflow can be restricted sometime due to long time of running, like I'm passing some coolant, so the pipe could damage. Okay, the debris will come, some thing will come which will blocks our inlets. So in case of our automobiles, when we are passing through hilly areas, okay, you will see a lot of leaves will be there in autumn season. So those leaves can come in front of contact of our inlet location. So those will be inlet, blocked inlet. So the whatever the quantity of air we want to intake, it will not be able. So mostly the air comes from the downside also of the engine. So you can see whenever you open the bonnet, there'll be hollow space below the engine. So to avoid that condition, what we have the other medium of taking in air. But still there are chances that there'll be some kind of dust will go or something, leaves will go, or we generally call it as debris. So which will restrict the our airflow. Then with respect to time of the component, like we know in our home location also, the motor has some efficiency. In the with respect to time, the coil will uh, reduce its life efficiency also. Even with respect to fan also, there will be damage could be possible. Sometime some rat will come and it will damage some blades. Okay, so could be condition. As of now, when we are designing battery, I am thinking of maximum output. But if we consider the worst case scenario, even the blade is damaged, or if there is a some reduction in speed, how much my battery will cool, that also we have to consider. So we have to think of all worst case scenario, even when the ambient temperature is very high. So in that, whether my air cooling is good or not. So those things also we can maintain, whether we have to provide the cabin temperature or not. If you see very hot weather, like in Delhi or UP, uh, we have like 45 to 50-degree temperature. Now, in that case, there is also we require more cooling to the cabin inside. Also, we have to need to cool off the battery. So, how we optimize the flow of a fan, so that we can have to optimize. And there are other operation like those things also we can part if we are transferring with the help of coolant, refrigerant gas. So what kind of gas we can have, so what is the maximum efficiency they can take away the heat, so what kind of gases we can fill in. So those things we have to consider when we are going with the cooling part. If we further go with the part, so we have further divided. So with respect to time, there are a lot of advantage and limitation. So if we talk about the air cooling, that is air natural and forced cooling. So simply we can as a student we can start with the basic concept. So we have a chamber, just I have just hidden that part. So air could be inlet and outlet, and hot can air can go from the other outlet direction. So the advantage we have, these are simple, easy to implement, and they are not that much maintenance. So that is our natural convection. So whereas there is some limitation, like we removal heat capacity is not that much high and not suitable for high power batteries. But if we talk about our simple case examples, our batteries in our home, so there we use natural convection. That's why you can see when we have the inverter battery, we don't put any fan specific there. Okay, so depends on the application where I'm going to use that part. Then we have liquid cooling, that we call it as direct or indirect cooling. So they the liquid coolant will absorb the heat and carry away with it. It could be direct or indirect. Advantage: high heat removal capacity, uniform temperature control, suitable for high power batteries and for compact system. So there is some limitation when we talk about when we have battery packs, the complexity will increase with respect to the cost wise. So how we have to provide these cooling channels? Okay, so we cannot take away heat from all batteries. So what should be the path of our coolant? So whether we have to go with the through pipes, heat sinks, jackets, or immersion cooling. So those kind of complexity will come when we are going with the immersion cooling. So if my mistake, there is some leakage, so the whole battery will get damaged. So those things we have to understand and we have to understand what are the requirements for our pump and maintenance part. Then we have the PCM phase change material that is very good, passive, no power is required, and it absorbs more heat as compared to uh, air and liquid cooling. So in this case, we maintain stable temperature for better operation. But if we compare with respect to this part, what we have, the PCB material have low thermal conductivities. Okay, and it is widely heavy and bulky. If we talk about, the battery weight will increase further due to PCM use. And if it is not well designed efficiently, the PCM will have negative effect also. So that's why PCM we have to use very carefully while performing the simulation. Then we have heat pipe cooling, where we have the heat sink as well as the heat pipes. Then we can add both things, air cooling as well as the PCM cooling also. So that we call it as hybrid cooling. So where we can add liquid plus PCM, air plus PCM, or liquid plus heat pipe. So the more we add, the more complexity will increase, and we require more optimization. So we have to optimize the best way, and the production time will also be increased because we have to make more complex design. And immersion cooling, it is easy, but it is very highly in cost and required complete sealing and maintenance. So whereas in this we can just go and we can reduce the maintenance, but in immersion cooling we require a lot of maintenance, regular maintenance. So overall, if we compare this part, we can say the immersion cooling is very highly costly, and the low cost is air cooling. And in between, we generally use medium range cooling. So either we go with liquid cooling or the PCM cooling. So depends on the application, we can go. And more apart from that, the chemistry inside the battery, that is very important. That also be a very part. So what are your selection guidelines? Like whether I have low power, or whether I require the low cost. So in that case, I can go with the air cooling. When I have high power and high performance requirement, I can go with the liquid cooling. When there is a maintenance free I required, and there is not that much high but passive cooling, is like we are operating some function and it is passive ways, like sometimes it is turning off, sometimes it's turning on. So in such case scenario, PCM cooling is the best. When we have very high heat flux, in that case we have to use heat pipe cooling time. And when we are it is running in the extreme condition, so that time we can use the hybrid or immersion cooling. So just like we have seen in previous slides. So I will go with that part first. So I'll just show you the model. I will open new workbench. So I'll showcase you single cell thermal cylindrical part. Then we'll go with the battery pack. Let me know if you have any doubt up to this point.
I think there is a question.
Okay. Just let me. I made a 2D box and fill with PCM font. So we'll discuss with when we come with the PCM part. Okay. So if you have, so you can save the file first. Save as. Always save your file so that we can extract the data if in case of there is a project crash part. So I will create a new folder, webinar, or battery cooling. See. Now we can take a fluid flow with fluent meshing, as well as I can go with the workbench meshing, that is fluid flow fluent. So let us go with the workbench meshing symmetry. So we can create the model in space claim or discovery or design modeler. So I'll go with CHT method because CHT will take less time to come to see the cooling aspect. Okay. So we'll select the XY plane. So you can go to design tab, 3D mode, sketch mode. So I'm selecting XY plane, rectangle. So you can draw a rectangle from center, 340. Okay, 240. tab, and length I will give 340. And the sketch, H for isometric view, shortcut. You can give the thickness 10 mm. Now select the top face. So I will create it as a cell. Create new component cell. So this is same thing we have done in the last case. So I'm just what I will do, I will add the cooling channel behind that part. So we have different cooling channel, zigzag for the normal cooling channel also. So just based on our design, we can create any design and we can provide the input. So I'm just selecting the top surface, sketch mode, front view. Now jet, rectangle. So I can use this same mirror. So just like last time, set as a mirror line. So it will create in both direction. Tab 42. I can specify the distance from this end to this end. 30. 32. And the sketch. Select the top face. Both you can select together. You can go to selection face with same area. So whenever we have multiple selection of same dimension, we can go with the selection part and we can select the same area. So I'm giving 40 length. So this is my P tab. So suppose I'm taking this as P tab and this to end tab. Create end tab. Now I can select the backside face for the enclosure. So the cooling channel could be of any dimension or at any location. So what I can do, I'm just creating a simple cooling channel for easy understanding. Sketch mode, front view. So whenever your view is oriented like this, you can rotate with the cursor. You can simply go there and click on that part. So it will orient your view. Now I can select a rectangle, select the first point and the second point and sketch editing. Now if I give 15 mm thickness. Okay, now this is like I have part. So somewhere you might have cross section at the inlet. Okay, for my this there is a part. So I can provide thickness and there is option P parametric. So what it will do in case in future if I increase my thickness of my cooling channel. Okay, so how this is like a single cell. So we might not see that much changes because most of it will take away from this direction. That surface area will increase definitely and there will be better cooling. So I can make parametric. So at different thickness, how it will change my cooling temperature. So that also we can study. So with respect to design, you can go with the parametric. So as soon as you click on P, it will display in the workbench. Okay. So you can see here a parametric set is added. So if I change the dimension in future, the thickness, it will do automatically. But we should keep only one design whenever we are doing parametric simulation. One design means only one fluid flow fluid complete setup. If you have multiple files here, what it will do, it will open each file and try to see whether I have applied to all cases or not. So whenever you're doing parametric simulation optimization, always go with a single case file. In that we can have multiple design point of views. Now done. So I will name it as cooling channel. Cooling channel. Now we'll give the namings. So I can use the same part here. So this is my structure cell. I'll select this cell and go to groups, create name selection, cell. Then we have the P tab, create name selection, P tab. Then we have enter. So we have option, I can select from the structure tree as well as I can select from the box selection also. Like you, if you double click on this, it will select the complete part. Just a second. Triple click, it is taking. Now groups, create name selection, enter. Then we have to provide this as a fluid domain, the complete cooling channel. So what I'm doing, I am creating the fluid domain part only, not outside the cooling channel. So what we have, you might observe that there is a, so I'm not creating that wall in between the cooling channel. And if you want to create, we can create, but I am assuming this surface as my cooling wall channel. Okay. So I'm not creating that part. So I'm just treating this fluid, solid as a fluid. So I will treat as a fluid. And this P side, I will treat as a inlet. And opposite side, outlet. Create name selection, outlet. Now we can hide other parts. Only I can activate the cooling channel. Select the opposite faces. Expect inlet and outlet will define other as wall. So this will define the fluid boundary domains. Okay. So we have four surfaces. Now we'll go to groups and create name selection, wall. Now this cell will have one wall also, uh, and this cell also have one walls. Okay, they, so we should not have two walls. So what we generally do, we use the shell topology for better node to node connection. And here also at the surface, as we discussed in last part also. So we have to go to workbench and use share topology. So it will connect the common surfaces and will have better node to node connection. Now press escape. We'll go to workbench. Yes. Now we'll convert our CAD model into mathematical model by doing the meshing. So in CFD, uh, we do the meshing with the help of ANSYS workbench meshing. So naming part we can do in the workbench meshing also as well as in the space claim also. Mesh, generate mesh. So now you can see with respect to this mesh, it is trying to align because we have used the share topology. If I don't use share topology, there will be different uh, mesh at this element and this. So that result it will solve. The solver will solve, but it will not give that much accuracy result. So let me show you the difference. If I go with this and I use unshare part, okay, and if I update here model, updates battery from source. Now if this is not required, I'm just showing if we use that technique, how we'll get the mesh, generate mesh. So you can see here, there is a separate mesh on this fluid block. There is a separate mesh on this part. So when we'll solve, it will solve, but it will not give the accurate result. The result will not be transferred. It will not take proper heat from the battery. So whenever you are using battery cooling technology, always use share topology so that whatever the heat calculation we are doing on the cells, those data can be transferred to this second cooling channels. So we have to use go to space claim, or if you're using the design modeler, there is also one option share topology. So we have to use share topology. Now, if I go with the update, it will generate node to node connection. So whatever you make changes in the geometry, you can update from here also. Okay. And you can do the changes. Now we'll generate the mesh. So let us take the size is in meter. So I can change the unit from the top mm. What I'm giving 1 mm. Generate. So if we are to do the parametric simulation or the grid independent studies with respect to the mesh element size, okay, what we are doing, we are refining with respect to the time. So generally, if I keep this as parametric, what will happen? It will change the complete mesh or all the complete all bodies. Okay, so you can make it as element size, and if I make it as 3, I cannot change here now. So whatever changes you have to do, you have to go to the workbench setup. Now, here you can go to the parametric set. Next time I can see my results at 0.5 mm mesh value. Okay, so how much there is a difference in the result. Same way I can go with the zero point 0.4, zero point 0.3. So at some time the result will be similar. So whenever you're using, if you have the part, you have to apply mostly on the all bodies. Okay, if it is not there, you want to specific refine at particular area where your major physics is occurring. In that case, you can go with the local method with the right click on the mesh, insert, sizing, and you can select that body. Like suppose I want to apply only this cooling channel. Okay, apply, and I can provide the size, and then I can use the parametric here. Then it will be parametric only for this particular part. Okay, so like this you can create for part. Since I selected the face, it has given the face sizing. If I select the body from the top, it will apply to complete body. So these are the selection where we apply body sizing, face sizing, and the head sizing part. As of now, we don't require it in our current case. So I'm just deleting it. I will generate the mesh. We'll check the names. Then we'll go towards our setup part. Now mesh. So you can see the names. Cell, C tab, N tab, fluid inlet, outlet. Try to have inlet from the positive tab sides. It is not compulsory, but it's better based on the real case scenario. Okay, so have the inlet towards the positive tab sides. Then this is like we have given the name. Now another thing we have to do, we have to go to the geometries, and we have to define this cell as my solid, because this is my battery case. Solid. Then tabs also as a solid. And if you remember, we are missing one point here, that is terminals. We need to connect our batteries with the terminal also. If I'm using battery model, I have to define, but in PCM case, I can skip that terminal part. But when I'm using cooling technologies, we have to define the name of terminal also. So that we can do in space claim also as well as here. So I will use the phase selection. So if you see, this is my N tab. So I'll select this phase and name it as N terminal. Same way I can select this phase and name it as P terminal. 4 external connectors. Done. Now mesh, right click, update. So if you want to export this file as a mesh file only, and you want to transport to another system, there is an option. You can go to file, export, mesh file. So you might have received sometime mesh file. So you can go with this a fluent input file. If you want to use any other tool like Polyflow or other tools, you can select the format here. As of now, we don't require. I'm just closing this. Now we'll go to the next step. That is our setup. Double precision and 4 number of cores. Start. Okay, so you can see the inlet, it will showcase the blue color, and the red color will showcase the outlet. So you want to show the mesh, you can go to the display and click on the edges. It will display the mesh part also. Okay, mesh view. So we should have minimum 3 element. Now we have good enough element for the better results. Now, if uh, I'm to solve both case, like, so let us take with the models. So for simulation, I want to solve temp energy equation, that is for the temperature, we enable energy equation. Even if I turn on the battery model, this energy equation will be also turned on automatically. Then viscous for flow analysis, I will enable the laminar flow. Okay. Then under models, battery model, I will enable the battery model, and then okay. Now, as we have discussed in the last session, we have different modules. So this time we'll go with the CHT coupling method. If we have different C rate, we can define the different C rate. So in PCM cooling, we'll go with different C rate. As of now, we are going with the CHT coupling for uh, prismatic batteries. Go to conductive zones. So we have to define the active component. Active component means where the reaction will take place. So that is cell. Passive components where there is no reaction, and these are our taps. So we have defined the name N tab and P tab, that is our taps. Then we have electric contacts, that is N terminal for negative taps and P terminal for positive taps, and we can print the battery connection information. So this is how we do for the single cells. Then we can give the voltage. Suppose I am having 10 watt, or last time 10 watt we got very less temperature. Let us go with the 15 watt, and current value, it will not have that much effect. I can take 10 or 100, apply, and okay. So I'm going with the steady state case. In transient case, we can see with respect to the time how much heat it is taking away with respect to time also. Now, since flow is a laminar, if you we can see if gravity will play important role, we can enable the gravity also. So this is like simple case scenario, it will not have that much effect. But if there is a cooling channels path different up and down, like in the backside, if we create, then gravity will play important role. So for current case, if I am to define gravity, I can define the value, or I can define the function also, that is with the help of uh, with the function 9.81, or you can define the expression minus g. So we have two option. So gravity also it will take, or I can simply define the value also. Okay, now minus g means gravity value in terms of minus y direction, downward direction. Then we'll have to define materials. So first we'll define material for the air. So if you want to pass air through this cooling channel, we keep air. If you want to pass water liquid, so we can go to the Flint database and add the water liquid. So we have multiple materials, like suppose you have some chemical. So there are some chemical gases also on the top. You can use those chemical also. Just like if you have some gases properties, you can define those property. If you have the multi-phase medium also, you can transfer those part. So rest cooling part will play as a CFD part, mostly just like generic CFD, whereas the battery will have to select the battery model. Now we are using currently as a water, OP, close. Now in solid, we have to define the E material, that is electrolyte material, aluminum, E material, density I'm taking 2092, 678, 18.2, and this you can keep defined per UDS 9.1 e to power 6. So this UDS you can take as a reference. So this is 1.1 19 e to power 6. Okay. So when we use C rating, we have to define two for potential, for positive phase and for the negative phase. Now we are using CST, so we can directly give the direct value, constant value also, or we can use the UDS part also. Now if you want to use aluminum, we can keep no. If you don't want to use, we'll keep that part. Same way, if you have different material for that cooling channel, you can add that material in the solid part and then you can assign. So we'll go to cell zone, cell, edit. In this case, what we are using, we are giving the voltage and we are using a battery model. There we have another option, like I can define with the source term also, and then I can define the heat generation from that part. So we have two approach, both will give almost similar results. But when we have this kind of battery model, it give more accuracy as compared to this kind of heat source. So mostly we have observed that a lot of researchers, they are using this source term instead of giving the battery model. So that source term we generally use in case of PCM model when we are using solidification and melting. Whereas if I'm going with the cooling part, we should go with the basic default this purpose. Okay, with the help of battery model. Now we'll select the material for the cells, that is E material, apply, close. Then in fluid, we have to assign water liquid. So we have to need to change from air to water liquid. Now in tabs, we don't need to assign anything. By default, there is aluminum. So if these tabs are of different material like copper and aluminum, then we can add the material and we can assign here in the tabs part. Done. Now we'll go to boundary condition. So we can select with respect to the boundary types, inlet, and so we can give the velocity at which the fluid is entering inside the fluid domain. So let us take 0.01, apply, and the temperature. So temperature is very important. At which temperature the water is coming. So it could be natural water, natural flow, or if you are providing some coolant water, like I am giving some water at 20 degrees Celsius. Okay, so you can apply, select the units, temperature, degree Celsius, close. So it will change to from Kelvin to degree Celsius, and I'm suppose giving some water at 20 degree. So generally, depends on the condition. If you have giving coolant water, what you require a cooling source also from where you are taking the water. So generally, on with respect to the ambient temperature, we'll get the temperature. So we can keep default temperature also around 30, 35. Or if you have the coolant, you can use the coolant. So the more the lower temperature, the heat will pass. Okay, because the delta T plays very important role when we are passing the absorbing the heat from the battery cells. Apply. And if you want to vary this parameter and you want to see the battery behavior with respect to the temperature change. So what you can do, you can as input as a new parameter. Okay. So now this coolant I want to use as a input parameter. So next time if I want to give 30, I don't want to change anything. I just want to see if instead of 20-degree water, if I go with the this unit. So you can change to degree Celsius and you can go with the 15 degree or 25 degree. So how much changes will be there? So what we can see, we can save a lot of money with respect to the coolant process. Okay. So that way we can do the parametric simulation with respect to the temperature. Okay. Same way, if you go with the velocity. Okay. So as of now, when I'm going, I have to remain in the laminar flow range when I'm selecting as a parameter. So again, you can create as a new input parameter 0.01. But once you reach to the turbulent model, so there you have to select the turbulence model, viscous model, which is not parametric. So sometimes we have seen observe that students are doing parametric simulation, but when they are going with the speed, sometimes they use the laminar velocity and somewhere they will use the turbulent velocity. So it's better to use K omega L model, transition model for laminar to turbulent. But as of now, you can make this parameter also as a parametric. Apply. So when you are giving this name, you can change this name also like you have seen here. Edit. Expression new parameter to apply. Close. You want to rename them, you can rename in this parametric set also. So this is my parameter 2, parameter name, velocity. So you can understand what you are giving and where you are giving velocity at inlet. Okay. Same way, this is inlet temperature. It will help you to understand also, because sometimes when we have multiple input parameters, we will get confused which parameter I have given, parameter 1, parameter 2. Some parameters are easily to understand, but if we have 15 to 20 parameters, if we don't know the name, then it will be difficult when we study the graph chart also. So as of now, we'll go with this part that we have defined. Now outlet will keep gauge pressure as 0. We are keeping this open to ambient. Okay. So we'll go with the outlet. Gauge pressure 0, thermal, will keep default, apply, close. Now we have to provide the condition at the cell wall. Now some have the option to that I want to see change the environment convection coefficient also you want to vary. So there also you have option. So whenever you want to have any variation, you can go with the new expression and you can define the value. Okay, you want to change the ambient temperature. So instead of repeating complete setup again doing lot of times, what we can do, we can use the expression and I can vary the ambient temperature. So let me take this ambient temperature as a new input parameter, and I will name it as ambient temperature. Ambient. So if I keep my inlet flow same thing and I want to see with respect to ambient condition, how whether it will be there or not. Okay. So you can keep that part. So let me give the value. So ambient temperature I'm keeping 30. Okay. If you want to use some function, you can define some expression also. There is some function also while giving the expression also. Okay. Now heat transfer coefficient I'm giving 5. Apply. Now I want to copy this condition to all my cells, other walls. So you can go to copy, cell fluid, copy. So we'll copy from this cell wall. So you can see we have copied from the cell wall. Same property I want to assign, same parameter to this boundary zones, surface, wall of fluids and the wall of taps. Copy, copy. Now it will copy all condition with same expression parameter. Okay, ambient temperature. You can see it is copied. Now we have applied the boundary condition. We'll go with the next part. So these expression part are optional. It is not compulsory, but I just want to showcase you the parametric simulation. That's why I'm doing that part. Now we can go with the. So since we have created the parameter, we need to check with respect to the output also. So for creating output parameter. So if you see in the workbench, there is no output parameter as of now. Now, if we want to create the output parameter, we have to create output parameter with the help of report definition. So we'll go to the report definition, right click, new, surface report. We can check for the mass flow rate. So if I increase my thickness of my cooling channel, how the mass flow rate will vary. Mass flow rate at the outlet. Okay. Even I, so if you see, I have created the parameter, but I have not selected the output parameter. So until I have created, but it is not. So you have to create this create output parameter, then only it will be reflected. So I will just show you. Here you can see I have created the report definition, but it is not showing. Once I click on the output parameter, it will create the output parameter. Okay. So now we have in workbench mass flow rate at the outlet. Okay. Same way I can create another with respect to the temperature. New volume report maximum of temperature. maximum temperature, and I'll select the tabs and the cell. I'm not looking in the fluid, I'm looking at the battery. So if you want to know the temperature uh, of this maximum, you can create that part and click on the create output parameter. Click OK. Same way you can create multiple report definition and it will add a little bit computational time, but you will get the input. So we can see the velocity at the outlet also. Okay, if you want to see or the pressure you want to see, you can see the pressure also. For that you have to create report definition and you can see the variation of pressure value also. So you can go with the new surface report area weighted average and then pressure at the inlet. So to maintain that velocity, pressure at inlet, and you have to select the create as output parameter. So I'm just creating this only. There are multiple options. You can go with the battery variables also like voltage, all those things. As of now, we'll go with an initialization and then initialize. Mm, when we are doing parametric simulation, first we have to run a one case, then we can go for the further run. Okay, so I'll just show you. So suppose I don't want to run it completely like there'll be float residuals. We have to vary because this energy will go very high up to 17. We can go 17, 17. Okay. Now again I have to initialize and calculation what I'm giving here. So sometime in initial case when I'm having the nodes different or the thickness is different. Generally, what we have observed that some students have using parametric simulation, but here they give only 100 iteration. So what happens? It will simulate up to 100 iteration only. But if you give more number of iteration, it will solve till convergence is not reached. Okay, so always you can give more number of iteration to see the complete convergence behavior. So as we are out of time, so that I will give not that much iteration. I will go with up to 100 iteration, but it will give us some output value. Okay, calculate, but you don't have to use 100. You can go with respect to your convergence condition, like you can give 1000 or 5000. So once it reach convergence, it will stop before that all only. Then last time like we have did the part the temperature contour, we can create the animation part in the calculation activities and you can see. So this is pressure plot, then this is our mass flow rate, temperature, and pressure at the inlet, and this is our scale actual graph. So this is on the top we have content equation, then we have momentum equation and energy and CST. So these are the battery equation. UDS. Let me see if any other question. How can required cooling load capacity be estimated? Okay. Cooling load capacity we can estimate before running the simulation, but we should know like the design. With respect to the design, we can go with the part like what is the voltage it will generate and whether we are giving the pack and series connections. I'll explain you this in upcoming slides. Yeah, for every parameter, there will be not separate case file. It will create a file, output file, where it will store the data for each case file. So now if you see in the workbench, you can see I have created the three output parameter. So once I solve this, it will keep the data. It will give the value at the here condition. So we need to do post processing inside the Fluent tool or inside the CFD post. That is post processing part. But if what I have the advantage, so instead of repeating complete setup for each different case, what I can do, I can simply keep the values here, and I can see which case will give me the best output. So those things we can study here. I will just show you two cases. In this case, even if we turn off the energy flow equation, you will see the temperature of the battery will also be very less. The main reason is that because even if we are not flowing the battery, the heat will pass through this surface area. We have added the more surface area to take away the heat from the batteries. So sometimes depends on the battery. So the thickness and the dimension of this cooling system also plays very important role. Sometimes what we have, we might have some blockage or we might close. So nowadays the engineers or the researcher, what they are doing, they are enabling the battery cooling at particular temperature only. So that we used to do with the help of UDF code. But prior to that, it will also take some heat from the battery also when it is connected, because heat will transform with the help of conduction from one battery to the cooling channels. So we are getting almost with the help of that cooling, we are getting 21.7 degree temperature because of coolant. Now, if I will increase the temperature of coolant, we will see increase in the temperature. So we can see the variable parameter one by one. Okay, for our case also, I think it is converse. Okay, it is not converse, it is stopped at the 100 iteration. So because I have given the 100, but if you further run, the residual plot will come down. Okay, and it will converge after some time. Now I can check the temperature. 1, 2. Can select the volts, save and display. Okay. Or if select all, so you can see at the inlet side we are having. So if I show only the inlet side, this is my temperature. And if I take cut plane of this, okay, since our flow is laminar, I can create a new surface plane. I can change the direction ZX, XY. Now this is at the center of the cooling channel. Close, and I have created new surface. XY, create, close. Now plane this. Okay. Global range, motoring, set display. So major it is having 20 degree, but if you see the outlet, it is taking away heat from that batteries. Okay, this is at the center. So if we go towards that part, we'll have that part. So let me see with the complete part. So in this complete fluid domain, the water is 20, but most of heat is coming from this surface. Okay, and we are getting 21 degree temperature. So you can see there is a cooling at this side. Some heat is taken care by the coolant. So we can check the pressure at the inlet. Okay. Range. Outlet we have given 0. So high pressure to low pressure fluid passes. So this is high pressure. And if you want to see the vector, at the plane 70 speed. So this is velocity vector. Fluid is moving from direction. Okay, since this is laminar flow and this is simple channel, we can see the vector. So if we have something circular motion or something, that I will also show you one case how the fluid is moving. So this is simple technique to simulate our single like cooling part also. Now, if I have done without cooling channel, the temperature would be around 50 degree or 48 degree. So there is a big difference in the coolant part due to more cooling area. Now let us see the temperature at the outlet. So this is temperature. Now we'll go with the parametric part. So I'm just closing this. You can save this file, save project. Then we can see the battery variables in with the help of C method. Like when I give C ratings with the help of models at different C rating, how the temperature will vary. I will explain you that also how we decide the C rating and how we give the input. Okay. First, we'll complete this single cell. Now, in this, I've given the inlet temperature 20 degrees Celsius and ambient 30 degree. Okay. So if we know if what is our major purpose here to whether understand if I'm changing some parameter, the result should also change so that whatever it is governing our loss, it is well captured. Okay. So showing Kelvin, pressure, mass flow rate. Okay. So retained data means it will save the file in the background. So if you see this battery cooling, we will go to this folder. Minute to battery cooling. This is the file DP. We have one fluent file. Okay, triple F fluent. And this is the case and data file, which is coming automatic outlet. And these are the output file for temperature, mass flow rate, and pressure file. So this file will be there. We'll get the data. Now, when I'm running for other cases like parametric, suppose I want to change the temperature at inlet. Suppose I'm giving 40 degree. I don't want to vary any other parameter, just want to change the design. Then I can click on retain data and I will update these results. Update selected design points. So I don't need to set up again complete case scenario. Okay. During the case of in this scenario when the inlet temperature is changing. Same way when I vary the element size. Once my design condition is reached, then I can go with the grid independent study with the variation in the element size. So how much result will change? So it will take some time. So I will just after this, I will add another 2-3 parameter. Then we'll run it. Then we'll come back to this part and we'll see the changes in the results. Okay. So as soon as I created parameter 2, you will see another folder will be created. Okay. This is DP. Now, if you go with the battery cooling, DP1 will come. Okay, this is for our second case. So this will be file for all these cases. Well, since we have mentioned the retained data, so we'll keep saving our files and the data in the background folder. Okay, if we don't keep this retained data, then we cannot do processing. We can only see in the workbench the values. Okay, so we'll go to the presentation now in the meantime. So this is with respect to the part. So we have, we can take one small example. We have a cylindrical cell, just like we did last time, which is a diameter of 18 mm and the length is 65 mm. So we call it as 1865 and O signify 0 signify the cylindrical. So this is not 0, this is O. Okay, so nominal voltage we have taken as 3.6 volt. When it is fully charged voltage, it is taking that as a 4.2 voltage. And the capacity of this cell is 2.5 Ah ampere per hour. And internal resistance, it's vary from 20 to 50 micro ohm. And weight, they have given 45 grams. So this is general data we get from the any cells. Even if you see some paper also, you will get this data. Now I want to do the analysis of this cylindrical cells and optimize, like if I make 3S 3P connection, or how should I make connection, like whether I should go in the parallel connection or how should I go in the series connection. So that depends on the connection type. So when I go with the series connection, the voltage will add. So if I want to increase my voltage of batteries, then I have to go with the series connection. If you want to maintain the voltage same and increase the capacity of the cells, we go with the parallel connection. So you can see in when I'm having the series connection, the voltage will add 3.6, considering as a single, the total voltage will be 10.8 volt and the capacity will remain 2.5 Ah. When I'm connecting these cells in parallel, the voltage will remain same, 3.6 volt, and the capacity will add. So it depends on the part. So when where you have to use and what voltage you have to maintain, that we have to understand. With respect to that, we have to create the connection. So in this cell, what we have the capacity of 2.5 ampere. That means at 1 C rate, it will discharge completely in 1 hour. So with 2.5 ampere. When I want to discharge with 30 ampere, I require a current of 5 ampere. Okay. When I'm discharging in 20 minutes, that is 3C rating, I require a current of 10.5 ampere. And for C, 10 ampere in 15 minutes. So higher the C rate, higher the current we will have, and the higher the heat generation will be there. So that's why we have to understand the thermal point of view, at which current, what will the temperature. So this current value will comes with respect to the C rate. So if I'm going for a high C rate, that means I require more current. So that's why you can see the charger you have at your home. 5 voltage is also there, but you will see the ampere rating also, 25 ampere, 16 ampere. So AC we have 16 ampere switches we keep. So that to maintain. If I if I were 2 ton AC or 1.5 ton AC and I'm keeping normal switch MCB, it will melt our part and they will be sparking. So that's how same way with the batteries also, because battery stores the energy and there is a phenomena, electrochemistry. The chemicals will react and current will pass. So and that electrical convert into thermal energy. So we have to work on the thermal energy part. So same way we have created a connection 3S 3P, 3 cells in the series and 3 in the series. So total cells are 9. So the pack voltage is 10.8 volt and the pack capacity is 7.58. So if pack current is 30 ampere, that is discharge. So per cells I can estimate as a 10 ampere. So at 4C I will say, so I can divide by 2.5, that will be 4C. There is a formula for heat generation generally that we calculate, that is Q equal to I square R, and assuming the internal resistance. So we have to find out the resistance value. If it is not given on the cells, we can assume some in range between with respect to the properties of the batteries cells inside electrolyte properties. So because the resistance play very important, higher the resistance, more the heat generation. Okay. And current is directly square proportional. So more the current, more the heat generation rate. So uh, we are assuming 5 volt per cells in the series of pack. So total 9 cells are there. So total 45 voltage of heat generation. And with respect to the volume of 1865, we can use the formula volume and we can find out the heat source. So just like I mentioned, instead of voltage, if I want to give heat source H value in the cell zone condition, I can find out with this formula. Okay. And that will be around this much value. So when we have this high much discharge rate heat source, the performance will drop and the capacity might not be similar. So again, there is a heat generation issue will come. So that's why we go with the cooling purpose, and we can estimate the part and we can compare the temperature with PCM and without PCM. So I'll show you how we can create this model and meshing. Okay, so let me give open the, so I will give another run here if it is done. So now you can see the pressure is not varying that much, it is slightly changed, but temperature it is highly, so you can see there is an increase in the temperature. Okay, so if I increase the ambient temperature, the temperature should also increase. So you can see the variation. Same way, if I vary the velocity, it will not have that much effect, but if I give 0.1 and keeping all conditions same way if I keeping it as a ambient temperature if I'm changing like 20 degree. Even I'm keeping the here I will keep like 25 and then I want to vary the size, that is thickness. Suppose I want to vary 20 mm. Then if you want to vary all parameter together, that also you can do. Suppose I want to have thickness of 18 mm, mass element size of 0.5 and inlet temperature 25, velocity 0.01 or 0.2. So you can vary all input also. It depends on you how you want to part. So once you do that part, then you can run one by one all together. So there is option. If you run one case, you will have the time. You can rethink and you can change that part. But if you click on update all design point, it will run all point. Now, if you want to retain the data, you have to click on retain option. Then update all design points. So this way you can retain all your design points for that particular case part. Now in the meantime, so what it will do, but always remember we have to do this run whenever we are doing parametric simulation. Only one case we have to consider. If suppose if we have cases like this, I have two case files. If I run parametric, it will open this case also and it will take a lot of time and the system might get hang if you have some high mesh and problem at this second level. So always whenever you're doing parametric, always run one case in a single workbench. Now I'll show you the battery pack, how we have to create. Okay, so let me open the space claim. Design tab, sketch mode, and view. So I'm just creating a simple example, 18 mm diameter, dimension, in hand sketch, length 65. Now I'll select this face, go to sketch mode, front view, circle, 6, 4, or I can go with 6 also. 6 mm. So this is one combined. You can make it separate also. Like this will be my cell, this will be my tap positive tap zone, and bottom will have the negative. So even we can create some connection on the top. So I'm just showing the small by cleaning up the small model. Okay. So I want to create a pack of 3S 3P. Okay. So we have two options. One thing is like I created tap connection, which is will take a lot of time to create the modeling part as well as then to assign in the our simulation setup. So what we generally do for such case scenario, we use the virtual connection, which will help us to run our simulation more faster way. But for that, we should have to create one tab also on the top side. Okay, so first I will show you this simple case. Then let me, if I want to copy this cell, so I can name it as cell 1, rename cell 1. Okay, now you can select this cell 1. You can go to move command and press control key. So control key, what it will do copy and paste. So I want to go in X direction. Suppose I want to give distance between to them 20 mm or whatever the distance you want to keep, you can keep that part also. Then again select the cell 2 Keep pressing control key. Again, you can give the distance 20 mm. Done. So this is 3S. And now select all together. Press control key and you can give the distance 20 like this. Then you can select from like this here also all together. Control Z. Press control key while moving with the mouse. So control will means it will copy and paste. If you simply move with the mouse, it will not that part. Now this is my 6 cells. You can rename them and you can define the naming proper. Now to create a PCM part, what I can do, I can go with the bottom part, select the surface and go to sketch mode. Front view, Z, rectangle from center. So I can select this domain and I can give 70 by 70 or whatever the dimension you want to keep. Then keep that part there 70 by 70. Now end the sketch. Now select this face, go to no merge option and we need to pull this to like this and there's option up to command up to this top surface. Done. This is, if you unhide this, this will create a PCM part. Okay, so this part I will treat as a PCM. So I can name it as go to new component PCM. Okay, then you can go with the particular single cells one by one. Then you can name it as. Okay, then rest cell you can copy and paste after you resolve this part, then you will get that. So this is, I'll show you first the battery part without PCM, okay, without enclosure. So I've created the virtual connection. So I'll just open that file. So we have 1C rating. So I'll just open this case. I hope you got idea how I'm creating the PCM. I'll just show you the model also. In current case, what we have taken, I have created the tabs. Then we have used the fluent meshing technology in this current case. So whenever you start with any cases like with battery pack or those things, you will find one more challenge option is that when I'm going with 1C and 2C, I'll get result with the steady state case. But if you go with the 3C, there will be sudden increase in the temperature. So in that case scenario, we cannot go with the steady state case. We have to go with the transient case. Okay. Same way with the 4C case. So how to stabilize our setup? So what generally instead of directly going with the battery pack, what is recommended, you go with the single cell and change the C rating because this C rating will not have any other things. Okay, is showing something like already run. Okay, I'll just show you. So what we have here, we have 3S3P connection, cylindrical cells, and we have used the P tabs and the N tab. So I will just show you in the display N tabs. So these are my cylindrical cells. Active zone. display. So these are my cell. Okay. And if I see the tabs, that is n tabs. Yes. So now on top, and the coupling wall is also wall steps. N tab. Display. So these are my n tabs. And if on the p tabs we have display these parts. And on the top we have the cells. So I hope it is clear. So this is we have given the name and we have created the p tabs, n tabs, and these are my cylinder. I'm just selecting all. So if I go with the connection in the series and parallel connection, the terminals, it will take a lot of time. So generally, how do we connect? When we have series connection, we connect positive tab to negative tab and negative tab to positive tabs. When we have parallel connection, we connect positive to positive and negative to negative. So we have to sometime we have to alternate the cells also to create the connection. So it's better way what we do, we can use the virtual connection. So virtual connection, we have to create a file. So in this case, you can see what we have done. We have enabled the battery model, MSMD, and NTGK model, 1C rating with 6 Ah capacity. Okay, so when we are going with the that part battery pack, the temperature will also shoot up, even in 1C case also because of battery pack, because we have increased the capacity. Now in that case scenario, if I apply this condition, this stoppage voltage, it will stop my run within some iteration. So what you can use, you can change the criteria condition from voltage to SOC. So SOC we have to use 0.05 and 1. Then these are my conductive zones, active component cells, passives are my taps and electric contacts. Here we have to use the virtual battery connection. So this is my file. So where I provided the connection. So I will just show you the file, virtual connection. Just a second. This is the file. So I have to define the connection, whether it is in parallel, how many in series. Then negative tab will connect it with the positive tabs, cell 1, cell 2. Like this, you can define the connection for the battery virtual connection, and it will save a lot of time for the computation of part. When we are going with the battery packs with respect to MSMD model. Whereas when you're going with CHT, you can directly connect. In prismatic battery, the connection are very easy to create. But whereas if you go with the cylindrical batteries, it take lot of challenge while creating those connection physically. So generally we use virtual battery connection mostly in the cylindrical batteries. Then we can define the capacity and resistance table with respect to our requirement. So we have specified the material, E material in the solids, E material, the properties with respect to the requirement, connectivities. Then we have assigned the materials in the cell zones. So each cell we have defined the E materials, and tabs we have defined the materials with respect to the tabs. Okay, so I will show you cylindrical. So E material, same way. So 9 cells, it is taking cell 1 as a cylindrical. So that's why we are saying C8, E mat. Then in tabs, we'll have the aluminum material, N tab, A tab. So you can edit all together also. Simply select all, right click, edit. Then we have the boundary condition where we provide the convection condition. So you can select with respect to zone type. Internal you can hide. Then walls you can select. Shadow is the coupling part which is not required. Okay. Then which are coupled, you don't have to provide the input. So you can select the walls. Only walls we have to define. Convection and free stream temperature you can provide like this. And when we go with the run, you can check the part. So in this case, what we have enabled, only battery equation. So if you see on the top, what we have viscous also modeling, but it doesn't matter. We can turn off these models with the help of control methods. In control, there is equation, and you can see I can check the flow and the turbulence. I am solving only battery equation. Now when we create the report definition, we can check the different variable part. So this is maximum temperature. So at each part, I can check And I will check in the report plot, maximum temperature plot. I can plot it. So with respect to time, okay. So in current case, once see the temperature is not that much shooting, but I am saying with respect to the time. So you can decrease this like float. Okay. So let's run for further time. Okay. So this transit simulation take a lot of time. That's why I kept the run file. Okay. So we can see the temperature variation with respect to time, how the temperature is changing. Okay. Slowly with the, so the smaller the factor will give, we can see the smaller graduation part. Then we can see with respect to the temperature contour. So in this case, we are getting temperature maximum around 30, not above that. And if you're running for further part, so this is, we'll get the temperature. So how do we compare? This is 1C, 2C. The contour will look like similar only. The you are seeing here the part. Okay. But only what thing will change, the temperature which you are getting here 29. It has taken some around 1500 seconds. Same temperature will come before in the 2C rating. Okay. So that's how we get the data and we compare in how much heating will be there if I go with the part. So that's why we say when we have 4C rating, the battery will discharge within 15 minutes. So those kind of simulation we perform. Now, if I open the 2C case, I'll show you that also. The setup is similar. Okay. Then this is for 2C case. Now, in this case, what we have just make the changes. What I have done only, I have just copied. So there is another option in the part. Okay, if you simply copy from here, it will copy the complete setup, because sometimes what we require, we might need to change some mesh if the solution is not stabling. So here in 1C, I can use a little bit coarse mesh, but if I want to modify my mesh, so if I only copy case and data, then it is will not be useful. So what I can simply, I can create a simple copy of like this. You can create a duplicate. So it will create a duplicate of complete your module. So will come down and then you can use as a different case. Okay. So you want to modify any parameter, you can modify like this. So it will be copy like this. So it will save your simulation time and the setup time also. So no need to set up again. Only the runtime will be vary. So here battery model is 2C instead of 1C. And then if we go with the plots, maximum temperature plot. So you can see within less time, around 600 seconds, I'm getting 29. Whereas in my 1C rating, I was getting around 1500 degrees centigrade, where I'm getting here 34, 35. Then temperatures keep on increasing with respect to the time. So like this, I can compare the data from 1C, 2C. I can export this data. So there's an option, file, export solution data, and then I can transfer this data in terms of Excel form, ACSI. In notes, it will give the value or that part. Also, there is option in the part also we can export in the JSON data file. From the output file also, I can get the temperature value at each cells. Okay, this is with respect to that part. Now I'll show you the when I added the PCM, how it has affected my cooling. So just like we created the part, same way we have model. Just a second. So this is with PCM. So same file I have taken, mesh file I have imported. Okay, after modeling that part, then I'll just show you the setup. So in this case scenario, what we do, we don't require need to turn on the battery model. Okay, so simply we can give the heat source. So for PCM, you need to enable the solidification and melting model. So in ANSYS Fluent, we have the model, the solidification and melting, which we enable. And uh, like this is the PCM we have, and these are the cells in the battery pack. So in this case, we have used the laminar model for PCM melting. Then we have enabled the solidification and melting. So these are the default parameters we have to kept. So if you want to see with more drastic change, you can increase this value mushy zone parameter. So mostly, so if we are pulling with some velocity like extracting in metal casting, then we need to activate this. Otherwise, it is not required. Just imply this model. Then what will do? It will ask the user in the materials to define the melting and the point temperature. So if you go with the E material, so this is our electrolyte material for the solid part. So PCM material we have to treat as a fluid material. So somewhere we have seen some videos people are using as a solid material also as the fluid material. So instead of using two metals, I can define my PCM as a liquid material because it will melt down. So PCM will select as a fluid material, will define the properties, specific heat, thermal conductivities based on the PCM materials property, and then that is important here, pure solvent melting heating capacity. These values are very critical, and the temperature, at which temperature it will melt, at which temperature it will solidify. So at 43 it will become complete liquid, and till 38 it is solid. Once it becomes 39 it will start melting. So those things we can observe. So we applied the condition. Now in cell zone we have to assign the material. So cells we have similar. So you can see multiples are there. So how to identify? Simply click on part and type star and cell. Or tab you can type tab. So it will select only tabs. Like this way you can assign select the filtration process when we have multiple option. Same way with the cells. Like modules are there. You can scroll it. You can go with the mesh view as is. This. So we have used the fluent meshing. So I've kept the meshing view also here. So at different view, we can go with the So generic mesh, here you can go with the boundary layer also near to the cells to capture the real flow behavior. Okay. Now you can assign the properties, cylindrical, add it. So we have E material and you can see the source term. So with respect to C rating, we have to define the value of energy source. Okay. So that we have defined here at different C rate, we have defined different heat source value. And with respect to that, we can get the temperature, report plots, maximum temperature plot. So this is how I'm getting the temperature of each cell. So how to activate this temperature of each cell? There is an option. When you go to the report definition, there is an option temperature like per zone. So you need to activate this per zone. So I selected the all cylindrical cells for the temperature as well as the fluid PCM, and I have checked the part. So you can see the with respect to the temperature, each cells I can find out of each part. So which is giving maximum at the, so we are getting maximum temperature at the center cells. So like this way we can identify the temperature. Then we can go with the contours, contour of liquid fraction. So once we turn on the solution melting model, then only we can visualize the fraction. So this is at particular time step. So one means it is completely melt, and where you are seeing some fraction blue colors, it is not completely melt. So we can see the melting process also from initial to end point. So at different time for that, what we do the post processing in the CFD post. So generally that should have file. So I will just show you sometime. So this is how we got the results. So we can compare the results of different C rating also at particular time. So for C we have run for 30 minutes and you can see the temperature contour at time at with different view also. Okay, you can project these views from the processing part. Then liquid fraction also how the melting is there at particular time. So and we can create the animation. So this is for 4C animation. So how the temperature is changing. So we can showcase the animation part of that control also with respect to temperature also. One is liquid fraction and temperature. Same way, if you're going for other cooling aspect, you can create the animation with those cooling aspect also. So this is 4C animation. So this is I have done with respect to slow time period. So in when we are creating the animation file, we have the option to create the replay speed slow and fast. So if you go with the slow speed, you can see more in better way. So how the it is. So the red color means the PCM is melting. Same way for 3C pack. So you can see in 4C in 30 minutes it was completely red, but here in 10 minutes 3C it is not completely melt. The blue color means it is still solid. The temperature is around 42 degrees Celsius. Whereas if we see in 4C we are getting temperature around 65 degrees centigrade. So like this we can compare the temperature variation with respect to different C rating and the liquid fraction part. So we know at higher C rate, the PCM will melt more within less time period. So this is 2C in the initial case. That is with respect to our ambient condition. Okay, so we can measure our temperature at each time. So whatever the time we want to check, we can give that time step size and we can store the value in that respective view. Now this was the cylindrical part. Now I'll show you the prismatic case. So what do we have? So I will just open the workbench. I have already the case file for prismatic cells. Okay. So I'll just open the model here also. Before that, I will show you the another case of battery. So let me close this. So I hope you got idea about the PCM. So just you have to enable the solution melting model and give the heat source. No need to turn on the battery model. So this is like advantage. But how to compare? You have to first run the battery pack, okay, with battery model, so that you can get the idea whether I should run it for 1C or not C. Because if my temperature range is higher than melting point is higher than that, the temperature we are getting, we don't need to run. Now we have, I will show you another case scenario where we have cylindrical part only. Just like we have the PCM cooling, we can have the liquid cooling also, where they have done the flow part only. So just like I mentioned that we can have. So in this, what they have, we have the parallel connection. Okay. They also, we have used the parallel virtual connection, and we have alternate the cells. It's not compulsory that we have to keep in same orientation. So that depends on the how we are connecting. So we have the inlet from here, and there is a cooling. So and that's we have created a part. So we are using turbulence model here, and battery model also activated. So we are using circuit network method with NTJK model with 1C rating. Okay. Conductive zones are on my cells active. Passive components are my taps, negative taps and positive taps. And then we have virtual battery connection, same like we have used there, we have defined. Okay. Now, whenever you have this information, you can click on the battery connection information. So this will give you the configuration of the battery. So we have battery in 4 in series, and parallel we have 2. So you can see 1, 2, 3, 4. These are connected in series, and 2 cells are in parallel. So to make proper connection in series and parallel, we have used the virtual connection files. Okay. Now we have defined the materials. That is, for fluid, we are using air as a air cooling. In previous case, single cells, we have used the liquid water. Then for PCM, we have used, now we are using air. In cell zone condition, we have assigned the material. For solids, we have defined the aluminum and cell material. Somewhere we use cell material, somewhere we use E material. Okay, so you can define those with respect to your part. And we have assigned the cell zone condition, the material condition, cell zone, solid. So if I take shell is outer cover of the cylindrical cells. So we have another surface, another shell outside the cylindrical part surface also. Okay, so that is cell. This is our active cell in the connection form series. So we have to give the namings like in such a way that 1S, 1P to understand. S stand for series, P stand for parallel. So this is in first series with parallel connection of one part. Then 1S, 2P, 2S, 1P. Like this we have to give. So we are 4 in series and 2 in parallel. Now you can see we have assigned the material. Then we went to boundary condition. In boundary condition, we assign the convection coefficient and free stream condition, temperature, ambient temperature condition. Then we have run here the flow part. Okay, so you can see the control. So for solution stability, you can use this transition factor, and we have turn on the equation for the battery purpose only. But before that, we have run the flow part also. So you can see I will show you the animation of contour. So like this, you can see the velocity variation at this, how the velocity will vary. Same way you can check the vector also. So you can, if you want to see with respect to cells, what you can do, you can click on the draw mesh. then that window tab will open, and then you can select the cells only, active cells, and I can use the transparency option, display. Close, save it, display. So like this, with respect to this, you can identify the parts. So, but generally we don't require, but you want to visualize how actually the A is like. So in this between how A is going, and in between there is a slow velocity. Okay. So same way we can check for the vectors also and temperature also. Okay. So Romesh. So whether my each cell is getting proper air or not, is there a recirculation around the cell or not? That also we can identify. Okay, so through vector point of view, through air cooling, the cell should be come in contact, and this is outer cover. Okay, so this is cell. So from cell also it will take some heat to the shell, and from shell it will keep cooling with the help of air cooling. So this way we can do the cooling analysis of our battery cells. Okay, so if you give virtual connection, it will help us to have better battery thermal management as compared to connection. Mostly in cylindrical cells, we give virtual connection. That's why there is an option in virtual connection in cylindrical cells. Okay, so if we use battery model, that will give us more advantage and more accurate result instead of direct giving only heat source. We can use heat source also, that is also equivalent. But if we compare the accuracy, the battery model will give more better accuracy, because we have more variable, more electrochemistry behavior we can solve inside the cells. Whereas when I'm giving heat source, it will treat as a single generating source. Now we'll go with the that part. So you can see the temperature and other parameters, battery variables. Okay. So we'll go to our last part, that is prismatic cells. So I'll just show you the model, how they are connected. So in this prismatic part, what they have added the thermal pads. Okay. So when we ever go with the battery packs, we must use fluent meshing that will generate your mesh more faster way as compared to workbench meshing. When you have single cells and part, you can go with the uh, workbench meshing to have better connectivity between surface and the domain. We should go with the fluent meshing. So that is our current case. So we have this battery pack. Okay, we have the passive component bus bars, they are connected. So I will show you the connection, how they are well connected. Okay, so let me open the CAD model. So this pink color means they have applied the shear topology. So you can see we have 12 cells. Okay, so each, if I open one cells, only if I consider this one cell, I have one shell at the outer, then I have tabs, positive tabs and the negative tabs. Then I have copy pasted. This is my cells. So I have multiple cells, like 12 cells here, like this. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. Below these cells, since I was doing air cooling, yeah, still the temperature was not coming down. So what we can have additional step, we can use some thermal pads to absorb the more heat, because these thermal pads are costly in money, but they absorb lot of heat. You can see if we have electronic devices, okay, mostly in aerospace application, we cannot use fan condition or other those high speed condition. So what we generally we do, we use thermal pads or heat sinks. So thermal pad is a kind of good thermal management source. So this is thermal pad which is very small in thickness. So we should have proper meshing at this part. So it is around, if you compare, measure the distance, it is 0.5 mm. Can you see? So we have to do more refined measurement here so that we can have better. So these pads are of very small thickness and have very added advantage in the part. Same way, we have the bus bars on the top. So you can see this is my positive taps. Okay. So through this connector will be connected. So let me show you the connector, positive connect and the negative connect. So this is my negative connect. Okay. So if I select this and go to structure, it will be N tab, and this will be my positive tab, and this will be connected to the negative tab of the second cell. So if I open this again structure tree, it is connected to negative. So this is my positive, this is negative. Again, same way, this is my positive, this is negative. So this way I create a series connection. Okay. So like this we are connected, and this node P connect and connects. They decide our parallel connection. Okay. So this is how we connect, and below that we have a cooling channel also. So this is end plastic for the frame and cold plate. So in this cold plate, the fluid will move. So this is my fluid domain where my fluid is entering from this side, and it will come out and come out from this side. So this is how we are using for the wet pack. So this is, I have the sold case and that file, because this thing will take a lot of time for the meshing and the simulation. So our connection is 1 in parallel, 12 in series. Now in this case, we have used CST method, direct voltage we have given. So I'll just show you. You can give you can give, mostly we give equal voltage, but if you want to give variable also, you can give variable also. But to make battery proper thermal manage, we should give equal, because the battery should not charge or discharge unequally. It should charge or discharge equally. So we give equal kind of voltage. Just there is some issue in the thing. I open a lot of modules, so I'll just close some. Okay. Still solving. Okay, so you can see the values, how it is changing. Okay, ambient temperature if I'm varying. So how the temperature is changing. So from 30 to 25, there is not that much change because of what we are changing. We are keeping same only. Okay, the velocity I'm changing and the temperature. If I compare with respect to above temperature also. Okay, so those things we can identify and we can understand the data. And if you see in the background this table, so we have 7 modules. Okay, 1, 2, 3, 6. So these 6 files will be created in the backside. So if you go here, battery cooling files, DP1, DP2, DP3. So all cases file will be there. So if you are running for the transient case, then the transient file will be there inside the triple F folder, inside the fluid. So you can do post processing by taking this case and data file, and from the output file also you can find out the data. So that's how we do the parametric simulation and optimize the battery behavior. By varying the velocity or the thickness, we can see the change in the results. Okay, so the pressure is changing because whenever we change any cross section or the diameter, the pressure will vary. So if we see these 3 points, if I'm looking for the temperature, these 3 parameters will not change that much. So and that's how we avoid some parameters. So that we do with the help of there is option in project tree, OptiSlang tool. Okay, so that will cover in future how with the help of OptiSlang. So as of now, I have created some design parameters. So that will do in the design exploration. In case I have 50 design, 60 design. So what I'm doing, I'm running my time. I don't know like which design will give me the best parameter. So for that we do the optimization, which will help us to identify instead of varying this parameter. If you vary this parameter, we'll have the major changes in the results. And how much changes? 80% or 70%. That percentage graph it will give. So that helps a lot of engineers in the R&D when they're working on multiple input design variable studies to understand how the our parameters are critical and which parameter we should change. So let me close another. Just a second. If you have any question, please let me know. What is UDS? Why do? So UDS is nothing. It is the initialization stage where we use that user-defined function, mostly used for the defining the potential between the negative tab and the positive tab to start the flow of the electric current. How we can create a custom battery model which follow our defined energy equation and condition. So for that part, you can use the custom battery defined custom model also that is available inside 26. Okay, I will just import the file again. It is showing the error. So you can use UDF function to define your equation. There is a ACT also, ACS, which you can explore for defining your custom function. Okay, so I'm just will go in another 5 minutes. So I have shared this video, like you can refer this presentation, how to calculate the heat generation rate. So with respect to the formula, you have to calculate the part parameters, this formula, heat generation rate. So how you're connecting in the serial panel, based on that, you have to find out this heat generation value. Even if you, nowadays, if you use ANSYS GPT or the chat GPT also, will get the option. You just have to define your parameters, that part. That's how we have. Okay. So let us go with the final case and file data. I'll just import case and data file. So case means when we have the only file. So I can simply copy this location. So this is generally a module. Generally when we combine that part, so there is some error in this file. So I'll just check with that file. Okay. Or I can extract it again. Just give me 1 more minute. I will just import the file. Okay, it is still hanging. Actually, that run is going, which is taking the file size bigger. So I'll just stop the run, which is currently going on. So whenever we do parametric, it's always advised to like open only one case at a time, because it will close all Fluent window and then we'll start. So let me stop it. So whenever your system get hang, you can go to the task manager and to stop it. And you can see the CX file. So this is our Fluent part, which you can end the task. This is your battery pack. I can end this task. So So whenever we have this kind of scenario, what we have to do, we have to these bus bars. Generally, N types, P types we have selected. These are passive component. Even these bus bars, which we are selecting here, these also we have to consider as a passive components. And only in active component we have to consider cells. Other parts, tabs and bus bars we have to consider as a passive component. We don't need to add this outer part, that is a shell or these parts. These are not required. Only tabs, terminals and bus bars we have to define in the battery models. Because sometimes we have seen like students are defining that part also, so that will unnecessarily reduce the model. So it is not opening. I will just show you the results. So like this, you can get the results of battery variables and the temperature when we run these case files. Okay, the temperature and the heat source at the bus bars and the tabs and the temperature. And with the help of fluid meshing, we can get the meshing like this, and we can compare the meshing and the thin surface area. Just if it is opens, then it is hanging. So I will showcase in the next part session. Okay.